Okay, I just wanted to show the latest progress on the neural network. Um, right now it's written completely in C++, and it's trained on images from the Google Quick Draw experiment. The way that it works is it scans in this image directory and it looks for NPY files, and then it loads in images. These come straight from Google Quick Draw, and then it loads them in, and then it trains a neural network, just a simple feed forward neural network, on the images in these files. I'll go ahead and I'll give you an example. So let's see. Here it is. Let's see if I can pause this for a second. So here you can see it found banana, found cat, and found face and tree inside this directory, which is just these NPY files. The ones prefixed with off are ignored because they don't end with NPY. So it loads in 1,000 images from each one of these data sets. And then it creates two different neural networks. One I call a classifier, which is trained on taking in an image as an input and then classifying what type of image it is. And then I also have a generator, which is trained. That's this one down here. So this would be the classifier. And this is the generator, which is trying to learn what a face looks like, what a tree looks like, and what a banana and a cat look like, and then generating an image based on what I tell them, which one to generate. So here you can see this is supposed to be a banana, a cat, a face, and a tree. It's only doing 1,000 trainings, and the images are 28 by 28 pixels. And it's very kind of just a basic approach. I just, their error is based on, there's no like adversarial training. It's just the error is based on how off their individual pixels are from where I want them to be. Or if it was the classifier's training is probably a little bit better, where I say this is a tree. It knows that it's supposed to say it's a tree, so I can come up with error a little bit better that way. And then what it does is just go ahead and starts training them, and I'll let it finish and we can see what happens. Now each time the initial weights are different, so sometimes it trains very well, and other times it doesn't train that well. So you can see here it didn't really train that well. It thinks that it kind of gave up on trying to figure out what a cat was versus what a face is. Banana, maybe there's like a ghostly banana shape there, but it's pretty dead. Tree is pretty good. Let me retrain the network, and we'll see what it comes up with the second. See what it comes up with the second time around, and hopefully it's a little bit better. Like I said, I don't really train the generator that well. It's just, this project was originally a research project for school, and I was just researching properties of neural networks. I wasn't really trying to build a something that could generate images that well. This is kind of an afterthought, so it's not that great. Let me try it one more time. Let's see. Hopefully we get some good generation here. Let's see. Kinda. It's not great, but it's better. Can't get that banana. Let me try one more time for the banana. One thing I don't do with this neural network is save the weights. Like I said, each time the initial weights are just randomly generated, and I don't save them. So, sometimes I get a really good network that could generate all these images well. And like this one's even worse than the first one. It's normally not this bad though. Normally it takes like 3 tries that I can get it all 4 of them to kind of pop up, but we'll try again, and hopefully nope, not that great. Let me try one more time. Maybe I'll just keep trying until I turn off the recording and then it works. It's not quite the banana I was going for. Well, nothing actually generates a better banana than what a banana thinks it is. So that's kind of interesting. It thinks that nothing is a banana. Well, maybe we'll keep this route. Alright, so I trained the neural network a couple more times, and I came up with this for the results for the generator. They're not perfect. I mean, the banana is a little bit, not as good as I'd like it to be. I think part of the reason why the generator generates images that are really kind of crappy is because they're trained on a per pixel basis, right? So I say, here's an image of a banana, and then I ask the generator to generate me a banana, and if it doesn't generate me that exact image, it's going to have error. So things like, people draw bananas. You can kind of see people draw bananas this way, and they also draw bananas the other way. And because of that, there's that discrepancy where it doesn't, the neural network, it learns to draw a perfect banana this way, and then it's like, oh crap, I got to start drawing them the other way, and doesn't know which way is better because on average it's 50-50. One of the things that I thought was funny too with this time around, normally I can, with a banana, I get kind of one general banana shape that's a little stronger. And the general banana shape that I get is the same banana shape. See, if I turn off, right here I'm controlling how much of, it says it's 100% a banana, and then I'm reducing how much of a percent of a banana I ask for, and here it's asking just for 0% of everything. And so it thinks nothing is a banana. Normally this image is the image that it will produce when I ask it for a banana, but right now I decided to keep with this network just because it did generate the other ones fairly alright, and I'll be able to just kind of demo and show you properties of the generator. So up here is the classifier. It's done training, so you can draw into this box and have it try to guess what you draw. This is the generator, and with the generator it has these controls. I call these eigenvectors. That's probably not the appropriate term because they're not linear, but they're vectors of extremes, I guess. Here, it's generated a banana, cat, face, and tree. It's in the same order that you load in. It loads in the images. So banana, cat, face, tree. And you can control, again, how much of a percent it's a face. So like here, if I ask it to generate me 50% of a face, it, kind of looks like a face, but kind of looks like a banana. Because remember, nothing gives me a banana. And you can kind of just change these weights to figure out, like here's a face. And if we, like, let's say, let's try the cat. Sometimes the cat's kind of neat. If I decrease how much of a cat it is, and I start to increase how much of a tree I give it, eventually we'll get this kind of morph into a tree, where now it's 50% a cat, but it's majority tree, so it's still giving us this tree-like shape. And if I start to increase cat again and make it 100, you can kind of see it looks like cat's a little bit more dominant than tree. And if we back off the tree, eventually we'll kind of get this cat shape. So it's kind of neat just to play with these and see how the images kind of morph into each other. They're all kind of the smooth morph. Like here, I'll start to increase banana, and it does kind of turn from a tree to a banana right about there. And if I increase faces, let's see, you can kind of maybe, it looks like there's just too much junk here in the neural network, so maybe we'll back down these other ones, and eventually there we go. Starts to generate a face out of nothing. So it looks like, and we can actually turn the face into a tree. So it's just kind of fun to play around with it. There wasn't really any goal, like I wasn't saying like, oh, let's build a really good generator for this neural network, have a neural network that generates images really great. The goal was just to kind of research neural networks and the properties of them. Up here is the classifier. So with the classifier, you can draw an image, and then it will evaluate the image and try to tell you what it thinks it is. Now this classifier isn't great. The parameters for this neural network I kind of tuned for the generator because that was the last thing I was working on. But with because of that, the classifier's parameters aren't that great. So you can see the average error here is about 20-30%, so it's not great. And we can try to draw something, but hopefully it can kind of still work. So if I draw just a general face shape, it should be able to tell me that that's a face. And we can see up here, basically it's the inverse of this. They're different neural networks, so it's not the same neural network. There's two independent neural networks, but you can see here it says it's 0.8% a banana, 0% what was the second one here? I forgot. A cat face? I think that was a cat face. Hold on, let me put these back to their initial state so I can kind of see what they were. Yeah, so there's a cat, a face, and a tree. Yep. So you can see it's 0.8% a banana, 0% a cat, and 94.6% face, which is that's good, and 0.4% a tree. So it can classify faces. We'll try to give it I found for this classifier, because the bananas are, well, we can try it. I probably won't generate me a banana, but we'll ask it to generate me a banana drawn this way. That's a really crappy banana. You can see there it's 2.9% of banana, but it's saying 55% of face, so it thinks that this is a face, which is supposed to be a banana. I found with this neural network, it kind of looks for this kind of just round oval for a banana. No, it thinks that that's a tree. That's fair enough. Yeah, let's see if we can give it an actual tree if it thinks that that's a tree. 99.8% a tree. Maybe a cat. We'll try to draw in a cat here. Maybe 3 whiskers. I think cats normally have. Let's clean this up a little bit. And give it some eyes and a nose, something like that. And you can see, there we go, 99.1% it thinks that this is a cat. So it is able to kind of, but then again, 41% a face. So because there's definitely similarities between cats and faces. There are a cat face and a human face. So kind of interesting. It does kind of work. I did train up another before this. Like I said, I was working on the generator and trying to get that to kind of work, which isn't really trained that well. Realistically, what you'd probably want to do is have like a neural network train the generator, and have like an adversarial training where if it doesn't quite generate, because the problem that it comes up with, the problem that you get with this is, how do you delete this? Delete. There's a way to do this. New layer, delete. Yes. Okay. So the problem that you get with training the generator network is that, like, let's say here's the picture of a face that I'm saying, here's the smiley face that it's currently training on, right? Something like this, the image of the face, and let's see, something like that, and then maybe as a result, so like this is the answer that it's looking for, and then as a result, the output of the neural network is something that looks similar to this, but it's not 100% right. Actually, worst case scenario, it could be the same exact thing, just kind of shifted over a little bit, right? Something like this, where like if I were to overlay these two images, right, I'd have like, here's the actual original image that it was oh, this is really not that great, sorry. Like, here's the actual image that it was looking for, right, something like this. And you can see, even though it's very similar, this one in the background, even though it's similar to the face, because they don't quite coincide pixel per pixel, it's going to have a lot of error. And so it's very, the way that I'm training the generator is just kind of looking for features that overlap each other, that are similar throughout all images. And so for things like, I guess I closed it out, but for things like, faces, you kind of get that ghostly face circle with ghostly eyes, sometimes a nose. I guess I drew a triangle. My theory on that is I think people draw noses like this, or they draw them like this, and so it pieced them together and it draws the triangle, and then a smiley face. yeah, things like bananas, it's harder to train because with a banana, you know, you get people that draw them this way, right? Or you get people that draw them this way. So you do kind of see this general banana shape. Or you get people that draw them like this way, this like kind of upright shape that's maybe like a peeled banana, something like that. So you get kind of all these overlapping images, right? And so it's a lot harder to train it on what a banana looks like than something like a face, because a face has more of it's more universally drawn. As another example, what we can do is close out of this close out of the neural network and maybe train it on some other images other than a banana. So I've got some other from the quick draw thing. So like maybe instead of a banana, we'll train it on a butterfly, which you would think would have some more defined features, but it's still, people draw, I found the images of butterflies that people give it are very discrepancy, but you can kind of see there's like kind of a butterfly figure over here now instead of a banana, which is maybe it will train better because people draw butterflies more similar, and it does look like it trained a butterfly better. So like this would be a butterfly. Now if we reduce the confidence of a butterfly, it kind of transitions into what just looks like this general shaded. It actually looks like a face. The face performed pretty poorly this round. But you can kind of see it almost turns into like a tree and then a butterfly or something like that. It's just kind of interesting to see, you know, the neural network learn. And like I said, it was good for research. One of the other things that I also did is I had the images of the neural network trained. So here's some images. These aren't neural networks. This isn't the current neural network. I don't currently draw these neural networks because it takes, the program that I wrote to draw this is kind of slow, and with a lot of input, it doesn't really draw them. You know, it takes a long time to draw. So you can see here's kind of a neural network where green neurons represent actively learning. None of these, this network's been trained, so none of the neurons are really super actively learning. If we go to, like, here's an example of a young network that hasn't fully trained yet, and you can see that all of the neurons are kind of actively learning. They're all green, and that it's mostly listening to the most important weights are on the output. The information is fed from the bottom up. And so you can see most of the important information is on the output layer because the error hasn't fully propagated through to the front. But here's an example of a classifier that's been trained and the error has had time to propagate to the front. And you can, and also these neurons have had time to just kind of desensitize their learning rates. They become what I call stubborn neurons that are less sensitive to change. And you can see that you do get the inputs, you know, the image as a one-dimensional array, and you can start to see these properties of images kind of come out where I feed in the data, let's see, as a one-dimensional array. So you can imagine if this was my image, something like this, where it looks like this, where this is pixel 1, 2, 3, 4, 5, 6, 7, 8, and 9. This is going to be fed to the neural network and just a one-dimensional block. So it will be like pixel 1, pixel 2, pixel 3, and then pixel 4, pixel 5, right? And then this will go on. I should make Milton a little bit more responsive to taps. But this would go on until it would finally get to pixel 9 at the end. So with here, you can see the weights, they kind of make this fan type pattern, right? And the reason for that is because this image, right, if you think of like just a general image, most of the time people don't draw on this upper area of the image. They don't draw on the sides. They don't really draw on the bottoms. They really just focus on the center of the image. And I'm using the kind of the unprocessed images from the quick draw experiment, so they're not like, I know Google supplies some data sets where like the first pixel is always in this upper left region. I'm not using that data set. I'm just using the centered images. And so people mostly draw on this middle region of the screen, right? This area right here. And so if we think about how this one-dimensional array would look, where is the important information? Well, the important information isn't on the top. So this first kind of block is just going to be empty, right? And then as it's scanning across, it's going to say empty, 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 and then empty. And then eventually it will run into some important information for the sliver. So here we'll have like a sliver of important information, right? And then it goes empty again for a sliver. So we'll have like a sliver of unimportant information. And then it has important information again. And so you get kind of this effect where you have this kind of these sections of important information, and those correspond, you know, directly to these fan shapes, where like here's a block of important information, it's all being given to this one neuron. You know, here's a block of important information, it's given to this neuron. You know, and if you zoom in here, it's probably, I said just one neuron, but it's, if we zoom in, it's probably oops, let's go back. How do I go back here? Go, oh, come on. There we go. If we, oh, my pen tool is getting tricky. Come on. Okay, thank you, Google, or Microsoft. Work with me. Thank you. If we were to zoom in down here, we probably see that, yeah, it's not just going to this one neuron, it's also going to this neuron. Yeah. Yes? Okay. So it actually does look like this neuron's kind of the most important neuron in the decision process. This neuron looks like it has some influence, but the other neurons over here look like they're kind of disconnected from the whole thing. So this was an example of one of the classifier networks. The image of a classifier, I do have a classifier network that does kind of work better. Oh, I just closed out of, I didn't mean to do that. Okay. Here's an example of a classifier network that's, like I said before, I was kind of tuned towards the generator. This is just purely a classifier network. It's trained a little longer. Let's get rid of butterfly. Images. So we'll turn butterfly off again. And we'll ask it to just train on bananas, just so we can kind of have a more of a consistency. Okay. Thank you. So here's an example of just a classifier network training, and you can see like that's supposed to be a banana, or maybe it's a cat. That's probably a banana. And this is the image that it's currently training on, and this is the neural network. It's drawn in real time, and you know it's super blown up. So I mean it's super crunched down. This image is a lot bigger than my screen. So if I close this, it does train a lot faster. In fact, we can even close this out and just have the network focus on training the classifier. And it's also trained for about 10,000 images rather than 1,000 images. So it's trained for longer, and we can see that the error kind of does start to become less and less for each one of these categories. So I'll let that finish up training, and then we can draw some images in that, and hopefully it's a little bit better. Okay, so the network's been trained, and if we open up the drawing window here, now we're ready to draw into it. And hopefully this is the network that was just trained on, you know, classification. So it's probably a little bit better with banana. So if I draw a banana, something like that, hopefully, yeah, you can see here it says it's 99.9% sure that this is a banana, you know, 0.2% sure it's a cat face. So it's definitely more confident in bananas. If I give it a cat face, hopefully it will be able to recognize a cat face. And whiskers. Through whiskers is probably common. Yeah, 99.1% that this is a cat face, and you know, about 2% that it's a the human face. And if we give it a human face, we can see it's okay. Actually, it failed. This human face, it thinks that it's a banana. My guess, I take that back. It thinks that this is a tree. So let's try human face again. I think I didn't draw it big enough, but we can try it again. There we go. So it does think that this one, 98.7% a human face, and a tree. I mean, the general shape of a tree that it looks for is this. Something like that. 92.2% sure that that's a tree. So you can see that this classifier does work a little bit better. It's definitely more confident, and when it makes a choice, it's more of a like this is this. It has a higher confidence in the choices that it makes, and there's more of a contrast between what it guesses. Like it says 92.2% that this is a tree, and only mostly 0 for everything else. So a better classifier network, and my thinking again why the classifier trains better than the generator is just because I have a better way of training it. A lot of times I found out with these neural networks is it's really important on how you train them, how you give them their information. There's no recurrence, no ability to remember anything in my neural network other than storing information in its hidden layers. So when I give it information, I kind of have to the way that I give it information is influences how it learns a lot. Like I was working on text recognition, not text recognition. I was working on giving it strings of text and having it trying to learn, like how to construct a sentence. And there's a lot of different ways you can give them the sentence. You can say that each neuron or each input corresponds to a letter, and we'll just take the ASCII value of whatever letter divided by 255, turn it into a float, and then give that as the input. Or you could say, maybe each input corresponds to a letter of the alphabet, and then we turn on or off a letter of the alphabet, more of like a switch as an input. And depending on how you train the network has a huge influence on this. Also, because this is a feed-forward network and it relies on gradient descent, for a large part, I think that's a banana. That's fair. Because it relies on gradient descent for a large part, adjusting its learning rates is also important. It's dynamic learning rate, but it's learning boundaries, right? Like, if it has a maximum learning rate that it won't go over, and it has a minimum learning rate it won't go under. I don't want the neurons to completely die if I made the minimum 0, right? A neuron would never learn again. And that wouldn't be good because its data, might change, or maybe the neuron was very good for one specific type of input, but then my inputs changed and it's no longer, good for that input. So trying to, adjust the learning rates is also important. The number of trainings, very important. How long I train them on each input also makes a big influence. Like things with, you could probably see this on the generator, where if I go back down over here, here's the generator. If I make it so that the right now I say, okay, train each image is for a maximum of, each image can be trained for a maximum of 5 times. If I make this 1, let's say, and we run the generator again, you can see we start to get these blurred images where, there's just not enough time for it to learn the difference between a tree or a face. It just kind of knows that people draw in this general region, right? That's it. And so it just kind of looks for this general region. But it's blurry. It's not, there's not information here. On the contrary, if I make it so that like it was 5 before, if I make it so it's 10, now because my error is so high, I'll probably train each image about approximately 10 times for the classifier. Now you can see we get these much more sharp contrast between what it thinks a face and a tree looks like, what it thinks a face and a cat looks like. But what we also see is this kind of like it popping in and out of these different local minimums, right? So it's like the pixels are more defined, like with this tree. You can see that they're, it's more of a defined image of a tree. But we get this kind of like like here with a banana, it's completely forgotten what a banana looks like. No matter what I change its weights to, it just says, oh, this is nothing. You know, a banana is nothing. It doesn't know that what a banana is anymore, because I've never had it trained on you can think of the error as being this is just a calculus optimization problem. So, ooh, why is this opaque? Okay, let's try this again. So it's a calculus optimization problem, right? So like here's our graph of error, right? So this would be like some like weight, and this would be like the error. And we're trying to minimize the error, get to 0%. We'll never quite get to 0, but you can imagine our graph isn't necessarily monotonic. It's not. It doesn't. It could be whatever it wants. Like maybe this is what our graph looks like, right? And for error graph, depending on what a current weight for a given neuron is. So like with weight of n. And you can see, like in this case, these are very close, right? But I want my neuron's weight to be adjusted here so that it minimizes error, for its prediction. And if I make it, if I start my neuron, because the initial weights are just random, like let's say my neuron starts with a weight right here, so this is my goal, right, is to get over here. Oh gosh. So here's my goal. You can see it's going to look at the derivative of the error, and it's going to start rolling down this hill this way, being pushed down this hill. And I'll kind of fall and get into this local minimum, which isn't a global minimum, which, theoretically I'd want to be over here. So like, okay, this isn't too bad, but, what if I started, again, random, what if I started over here? Well, now I'm going to run into this error that's, it's going to fall down and run and eventually come over here. We'll start to oscillate around here. And it will do that if my learning rate is too low, because it's going to make very small changes to where the weight initially was, and it will kind of fall down into this minima. But if I had a high enough learning rate, right, if I'm taking big enough steps, like let's say if I take a really big step, and then I'm here now, and then I take another really big step, and maybe I'm just barely over this other peak, then I can start to roll down and find this more of a minimum, right? And again, in both situations, I never got to my goal. I would only get to my goal if my initial values were over here, which is why a lot of people spend they manually set they train their neural networks, and then they manually set their initial weights, because they can set it toward, maybe they don't know what the goal is, but they can put it somewhere like here, or they could put it somewhere like here and make it so that the neural network converges towards this goal. Even though they don't know what the goal is, they can get, close enough to it. And so with my neural network, again, it's kind of got a couple things fighting against it. One, it's randomly positioning the start each time, so each neural network is kind of different. Two, it's not being trained well. And three, sorry, to summarize why the number of trainings is important is because if I train it on the same image long enough, it's going to start to desensitize these neurons to learning, right? And when it does that, it will kind of slow this weight down. Like it will kind of, like, if we were taking, when we first start out, we start out with very big steps, right? Our neurons are all very desensitized. We start taking these big steps, and if we train it on the same image long enough, what it will do is it will find this minimum, let's say. We'll find this minimum, and it will lower its learning rate and make it so that it kind of sticks here. And then if we switch to another image, let's say another image is no longer favorable to be in that spot, the neuron weight wants to be in a different spot. Because it's desensitized here, it's kind of stuck on this image. Another problem that you can get is like these oscillations, where if like this is like what my error looks like, you can imagine that my weight just kind of rolls back and forth on this curve, right? And it just keeps oscillating back and forth and back and forth. That's one of the reasons and so it goes from a point of low error to high error. Well, I guess it would never technically get to this point. It would just kind of jump from here to over here. So you can get these like oscillations where it's always quite missing the local minimum. And in this situation, my learning rates are too high. I want to decrease my learning rate so that I can sink into this minimum. So it's a lot of work goes into just figuring out how to train these neural networks effectively. And all of the research that I've been reading up on are like algorithms statistically. A lot of times it's a lot of statistics to try to figure out how to optimize the data set, or how to optimize features that it looks for, stuff like that. I know with Google's QuickDraw they actually generate like a latent space of I think 178 different features that they are specifically looking. Well, the 178 different variables that they want the neural network to identify, and then they train the neural network not on identifying necessarily images, but just identifying these variables. And then once it learns what variables, 178 things it's looking for that differ between images and stuff like that, then it can start to use those variables to train itself even further. So a lot of the work is, the programming the neural networks, I don't want to say the easy part, but it kind of is in a lot of ways. And a lot of the work goes into, how to train the neural network. So I just wanted to kind of give you an update to show you where the neural network is. All of this is written in C++. There's no libraries used. I use math.h to figure out exp. It uses sigmoid activation function, and I didn't want to, no point in programming a Taylor series for E when you can just use standard IO. So, standard math. Yeah, no real libraries. I do use to run the main program. This code is kind of sloppy, but it was kind of this was thrown on top of the neural network. The actual neural network code, is a little bit cleaner. It's a little bit more straightforward. People will probably get mad at me because I don't everything's public, because I probably could have used a struct, but everything's public because I was researching. I wasn't trying to build an application, but I'll probably make this code open source, and hopefully this kind of just inspires someone to learn about neural networks or research them a little bit on their own. And for sure, I've got a lot more research to do, looking into like adversarial training and stuff like that. I know one of the things that frustrated me when I was trying to program this neural network originally is I was kind of looking for some, you read up on how backwards propagation works and stuff like that, and you get the math down, and then you're done with theory, and it's time to actually get to working on the actual program, and you kind of sometimes look for points to push you in the right direction. Like you'll start programming something and you're like, well, I wonder if someone's already done this in a cleverer way than I can think of, and you start looking for what's a good way to backwards propagate information through a network. And no, there's no information out there. At least I couldn't find any good information, because all of the information was like, well, just use Python, or just import this library. And yeah, okay, it's nothing wrong with using libraries and stuff, but if you're trying to learn neural networks from more of like a fundamental, maybe not like from a theoretical approach. Python's great for a theoretical approach, but more from like a programming them approach. It's no help. If I import someone else's code, I didn't really learn how to program a neural network from scratch. I learned how to import someone else's code, and maybe I learned how to train a neural network, but not how to actually implement one on my own. So that was kind of frustrating. So I kind of want to throw this out there just to give some people a point. And maybe this code isn't, obviously it's not great. It's single core. It's not multi-core. It's not programmed with Ray in mind. It's programmed with simplicity and just something I could push out in a week in mind, and something that I was using. But I'll put it out there, and hopefully if someone sees it, it will kind of inspire them to to build their own neural network, or build on top of this even, and just do something cool with it. I mean, it's interesting to see how much that this simple neural network can do. I mean, like I said, the whole idea of making it generate images was the idea of having it classify images was an afterthought, let alone generating images. That was an afterthought. And the original point, the only thing I really programmed this neural network to do originally was to learn, was to recognize patterns. So it was trying to, I'd give it input, and I gave just a simple sequence of numbers, 1, 2, and 3, and it was supposed to take this input and output 3, 2, 1, and then I also give it an input 3, 2, 1, and I wanted it to output a different output, would be 3, 6, 9. So I wanted to count by threes if it was given a reverse sequence, count by, I'm sorry, I said this backwards. This was not 3, 2, 1, this was 2, 4, 6. So it was supposed to count by twos if it was given an ordered sequence, an order sequence, and count by threes if it was given an out of order sequence. And and the neural network trained on this, and it worked fine with this. I noticed that my learning rates had to be a little bit more aggressive when I was training this network. Right now, even my learning rates for each neuron is pretty aggressive. There's nothing I can really compare it to because I don't really know, necessarily how the learning is done, because there's so much. There's different algorithm approaches on how you train these neural networks. But I think right now, for the generator, my maximum learning rate's 1.5, just as a scale, and my minimum learning rate is 0.01. When I trained it to recognize patterns, I had a maximum learning rate of 10 and a minimum of 1, and I think part of that was just to kind of jump over those local minimums. So I don't know, just it's fun. It's a fun research project to research. I wanted to throw it out there and see if anyone can make use of it, and if not, just have it for my own record. All right, thanks for listening to me blabber on, and let's see, bye.